First of all, a very warm welcome from my side. My name is Sebastian Hartmann. I'm currently doing my PhD with the Siemens AG and the Technical University of Munich. Here I'm part of the research group of Professor Peter Meyer at the School of Engineering and Design. Today's lecture is going to be about the digitalization of additive manufacturing. So within the next minutes, we are going to take a look at how digitalization is adding value in the entire process chain, from the initial product design to monitoring the real process in the end. The way this talk is going to be structured is that I will start with a general introduction of Siemens. We are then going to take a look at what Siemens is doing specifically in the additive manufacturing business. We're then dissecting the digital chain of additive manufacturing, and will then focus a little bit on process monitoring and control of one specific technology. So let's start with the general introduction of Siemens. Siemens, over the past decades, has built up a huge conglomerate of different companies within itself. And during the past decade, there has been a lot of effort to get some of the operating companies from within Siemens to the outside world. So this means that we set up several sister companies, several subsidiaries, and the two most important ones being the Siemens Healthineers, which focus on offering healthcare systems. The second one being Siemens Energy, which focuses on the energy transition. And with our Siemens AG in the center, focusing on the digital transformation of industry, infrastructure, and mobility, we are able to address the greatest challenges of our time. Myself, I work at the Siemens AG in the business unit Digital Industries. So therefore, the digital transformation of industry is part of my day-to-day business. For Siemens, one of the major aims, but also challenges, lies in the combination between its core business and the digital business. So Siemens came from being an electronics company. So where we grew a lot, where we were really good in the past and also right now, is in offering solutions, hardware solutions to automate machine, to automate processes. Over the past decade, the digital business of Siemens grew a lot. So this means, for example, our NX software solution, where you can design parts, simulate the parts, and so on, really took off a lot. And the goal and strategy overall at Siemens is to combine the core business and the digital business to one mutually reinforcing ecosystem. So this means that we want our core business to benefit from the know-how we now have from our digital business. But on the other side, we of course also want our digital business to benefit from our know-how, our experiences in our core business. And with this intersection, we are able to offer a really unique value proposition to our customers. If we take a look at what Siemens is doing in the AM business, the exact same constellation of real world and digital world comes into play again, because if you take a look at the portfolio that Siemens is offering in the additive manufacturing field, you will see, first of all, a lot of contents. But the most important one here is that Siemens is offering software solutions. So this means the digital world, and we are offering automation technology. This basically means our core business in the end. In terms of software solutions, within Siemens and Siemens NX software suite, you're able to be guided through every step of the production chain. So this means you're able to design your part with Siemens NX, you're able to simulate it with NX, you're able to send the data from the simulation into the machine, you're able to collect data from this machine and analyze this data in the end. On the other hand side, in terms of automation technology, it's important to emphasize that Siemens is not selling 3D printers itself, but we are offering all of the components that 3D printer OEMs need to build their own printers. So this means we, for example, offer numerical controllers that automate the movements of a machine. We are offering the drives you need to steer the axis for these movements. We are offering the industrial communication required with it. On top of the software and the automation, we also have value-add services in the additive manufacturing field. So this basically means we are offering consultancy services for the design aspect. So we help our customers design specific applications, specific parts for additive manufacturing. We also help them to build up their first AM factories and then to scale them up. And also we are providing financial services so that you can be guided through the scaling up processes by having solid finances in the end. So enough of the Siemens market show. Let's get a little bit more into the technology here, into additive manufacturing itself. For Siemens, it's all about bringing additive manufacturing to an industrial scale. And therefore, Siemens has identified 4 core technologies where this transition to industrial scale production has already taken place or will most likely take place in the future. The first technology in this regard is the powder bed fusion technology. Here, it's all about one or multiple lasers selectively melting specific powder particles in the powder bed. And by applying powder bed layer on powder bed layer, you are able to build up parts with powder bed fusion. Here we work together with EOS and TUM. The second technology is the so-called multi-jet fusion technology. Here it's not about a laser that melts or sinters specific powder particles, but here it is an inkjet agent that is dropped onto specific particles, specific points in the powder bed, and makes the particles stick together. And by this sticking process, you are able to build up parts in the polymer and also the metal sphere. Here we work together with the company HP. For directed energy deposition, the third technology, quite a different technology, because here you actually have a printer head, a so-called nozzle, that is able to move around the part freely and deposits material layer on top of material layer. And hereby you're able to build up metal parts subsequently layer by layer. We worked here together with DMG Mori, with Beam and other companies. For material extrusion, it's a comparable process to directed energy deposition, because here you also have a printer head that moves around freely. And the usual setup of such an industrial grade material extrusion system is that you have a robot arm where an industrial scale extrusion head is mounted to the end of it. With the movement, you are able to build up polymer parts. Most of the time, there are also some applications where material extrusion is used for concrete printing, so for building up houses. But for Siemens right now, the focus is on polymer applications with companies such as, for example, Seed and Stratasys. My own PhD and also the rest of this talk is going to focus on the directed energy deposition category right here. Because to clarify this, directed energy deposition is a category where multiple technologies can be assigned to. The technology that we will focus on during the rest of the talk, and is also the subject of my PhD, is the so-called laser metal deposition technology. The basic principle is that you have multiple powder streams coming from the outside of the nozzle, and those multiple powder streams basically meet at one specific location, so at one specific point. And at this exact same point, a laser beam melts the powder particles and basically creates such a melt pool that you can see in the video right here. The melt pool is then moved around. It subsequently builds up metallic components layer by layer. The most important advantages of this technology is, first of all, it has high building rates, which means it is quite fast in production compared to, for example, the powder bed fusion technology. And it also enables you to produce multi-material parts. So this means during one part production, or the production of one part, you can utilize multiple materials. So this is highly interesting for academia and business. The main applications of directed energy deposition in general, but this is also valid to when you just look at the laser metal deposition technology alone, is first of all prototyping and manufacturing. So this means, for example, in the aerospace sector, this technology is already heavily utilized. It's also very common to use laser metal deposition in repair and welding applications because you're able to build on existing parts. So if you have a part that is used up in a specific section, you're able to mill the section down and to build up this specific section using laser metal deposition again. Third big application is coating. So this basically means you're able to coat parts with laser metal deposition quite easily. And here maybe one quick story from my work at Siemens. We know of a lot of automotive OEMs that consider laser metal deposition to be one key technology for this coating process, because automotive OEMs are now obliged by European law to have a specific coating on their brake discs to reduce the wear percentage of those brake discs. And most of them look at laser metal deposition for the best possibility to make this coating on industrial scale possible. We've talked about Siemens in general. We talked about what Siemens is doing in the additive manufacturing business. And now I want to take a deeper look at the digital chain of additive manufacturing. And here I brought along one specific use case. What you see right here is a rocket nozzle. What this rocket nozzle does is when basically a rocket launches into space and it wants to get off the ground, it of course has to burn a lot of fuel. And the result of this fuel burning are of course a lot of hot gases, and those hot gases have to be released into the atmosphere again. And this is exactly what this rocket nozzle here is for, because the gas is flowing out of this hole at the end of the rocket nozzle. What we did here was that we designed such a rocket nozzle with specific characteristics that you were able to build up with additive manufacturing. So what we did here was we designed a double wall structure so that you would be able to inject cooling liquids in this double wall structure to cool the part while all of the hot gases are flowing through it. This was the initial design that we came up with. The next step in the digital chain after the design was to simulate this design. So this means we utilized a specific software within Siemens NX, and we simulated what would happen temperature-wise during such a real takeoff of a rocket nozzle. So we let all of the hot gases flow through the rocket nozzle, and we took a dedicated look at this double wall structure. We were working with liquid oxygen and liquid methane at this point, and we took a look at which specific sections a critical amount of overheating would take place. And as you can see right here, in the upper section of this part, there seems to be a problem with overheating, and also in the lower section, there seems to be a problem with overheating. We took the insights of these results and went back to the first step in the digital chain, to the initial CAD design of the part. We utilized several applications within Siemens NX and came up with a new design for those specific sections that you can see right here. If you compare this new design that is now based on the simulation results to the initial design that you see right here, you can see that there were some quite drastic changes, because this upper section, also the lower section, look different now. You have a different design, you have multiple insert chambers, you also have a different design at the bottom of this part right here. And this is how you're able to move within the digital chain of additive manufacturing. You're also able to reiterate design based on the insights you gather, for example, from fluid simulations. The next step in the digital chain is you have the part design, it's now ready, and now you want to test how this design would be produced in your 3D printer. And for this, we are again in our Siemens NX software suite. And what we did for this use case, we did not want to print the whole part, which is also possible, but we just took a look at a specific section, the orange colored section at the bottom of the part. And what we did now was we imported this section into our machine. So this is a machine from the company Beam. It's a French 3D printer OEM. We've imported, first of all, the design of the machine. We then also imported the design of our part into the building chamber. And then we take a look if this design is actually printable in the way we've pre-programmed it. So we are able to run the entire production process before the real process will ever take place. So this is all happening in this digital chain because we know exactly what the design is like. We also know what kind of movements the machine has to go through during the production process. And by that, we are able to validate if the design of this part is actually producible without any errors in the real process in the end. And with those insights, after you completely simulated the walkthrough through this entire production process,